We've now seen this idea of integration. Let's define it more formally. First of all, with what we call the definite integral. It all comes from the fundamental theorem of calculus, so what we call the fundamental theorem of calculus, which we did actually see at the end of yesterday. That idea is known as the fundamental theorem of calculus, and what it's basically saying is you differentiate the primitive function. Right? So the derivative of primitive function is the same as differentiating the integral, which ends up with the equation of the curve. That's essentially what it's saying. Some properties that allow us to play with integrals and manipulate them. Now, what you have to remember is an integral symbol is a grouping symbol by parentheses and so on, but it does have some special rules of its own. First of all, the actual idea of integrating a polynomial, which we saw, add 1 to the power over the power. A word on the notation, so again the long S symbol for integration. Once we integrate, we enclose that primitive function in square brackets. Some people use a vertical line on the right hand side, but more common it's square brackets. And the limits then go to the right hand side, but they stay in the same spot. So A was on the bottom, A stays on the bottom, B was on the top, B stays on the top. Factorising. This is where it's a little bit different. You can only factorise constants out of an integral sign. Because remember, you're going to integrate with respect to a pronumeral. So if you pull that pronumeral out of the integral, and you haven't integrated. So it needs to stay in there. So the only thing you ever factorise out of an integral is a constant number. You can do that, that's fine. It does not matter whether you treat it all as one function. If you prefer, you can split it up and integrate each individual term. And in reality, that's what we end up doing. You just integrate piece by piece. This one here, if you want to integrate from A to B, well, it would be equivalent to integrating from A to C and then integrating from C to B. Reason for that. Remember, you substitute the top number in and subtract the bottom number. So all of a sudden we've introduced this third number C. But in the first one, I would end up adding it in. In the second integral, I end up taking it away. So it disappears. So it's certainly possible to do it that way, and there are some functions, when we look at the picture, it's a better way of doing it. The integral from A to B is greater than 0. Hang on, what are we saying? No. If the function is greater than 0. That's essentially saying, if we're looking at the picture, if the curve is above the x-axis, we will get a positive number. The integral will be a positive number. That's what that's saying. And the other way of saying it is, well, if it's below, then I must get a negative number. Again, if we know what the picture looks like, we know if we're expecting a positive number or a negative number for our answer. Now, of course, if we're talking about area can't be negative, so we have to be careful with that. And we'll see that later, how we deal with those sort of things. Same sort of idea. I know that the integral on the left will be less than the integral right if, again, looking at the picture, the same thing as with the function. Again, if you think about that one. If what we're finding is the area underneath something, well then the area under the lower curve must be less than the area under the one above it. So if we look at the picture and we see that this g of x is above f of x, then we know the answer for the integral for f of x should be less than the answer for the integral of g of x. Okay, I'm integrating from A to B, but I don't have to do it that way. I can integrate from B to A, and sometimes there's good reasons for doing that. But if I swap those values around, then I must multiply it by -1. Because remember, it's the top one minus the bottom one. So if I make it the bottom one minus the top one, then I'm going to get the negative of the answer. So I need the negative sign out the front to balance it out. So you can swap them, but if you swap them, you change the sign. Symmetry. If you have an odd function and you're playing with symmetry, so you're going from -a to a, then that integral must be equal to 0. Because remember, what we just said was, if it's underneath the axis, we'll get a negative number. If it's above the axis, we get a positive number. So if I'm dealing with something symmetric, say for instance our cubic, if I was going from -2 to 2, the actual area from -2 to 0 would be the same as the area from 0 to 2, because it's symmetric. But the one underneath is going to give me a negative number, and the one above will give me a positive number. So when I add them together, I'll get 0. So if you know it's an odd function, you can save yourself time. You don't actually have to do any integration. You can just look at it and say, well, hang on, that's symmetric, it's an odd function, answer's got to be 0. You can do a similar thing with even numbers, because the symmetry on the even number, you would get the same. They're both going to be positive in this case with the regular y equals x squared. If it was underneath, they'd both be negative. But either way, they're going to be the same because of the symmetry. So rather than going from, say, -2 to 2, I can just go, well, I'll just work out twice from 0 to 2, because those areas have got to be the same. Why do that? Well, probably because 0 is such an easy number to substitute in. So if we go from 0 to something, at least one of my substitutions is going to be pretty easy to work out. A note on odd and even functions as a reminder: if you've got functions multiplied together, an odd times an odd will give you an even function. An odd times an even will give you an odd function, and an even times an even. So basically, if it's the same type of function, when you multiply them together, it'll end up an even function. If they're different types of functions, when you multiply them together, it'll become an odd function. And when I say multiply, that also means divide as well. When you divide, you're actually multiplying by the reciprocals. The rule's still the same. Okay, let's look at some examples then. 6x squared, we're going from 1 to 2. All right, I could factorise the 6 out on this one and just integrate the x squared. That's what we're really doing here. Add 1 to the power over the power, but then I can also now factorise the 1/3 out, and I'll have 2 lots, substitute in, 2 cubed minus 1 cubed is 14. That's just an example of factorising the constant out. The cube root of x, I need to put it in index form first. So when I put that in index form, it's x to the power of 1/3, cube root. Add 1 to the power over the power. So you see what I do here? Straight away, I'm going to pull that constant out of the square brackets. Tend to do that. When I'm dealing with fractions, if it's over that, well, that's the same as saying the reciprocal. So whatever the new power is, I turn it upside down. That's the number that goes out the front. So new power 4/3, out the front 3/4. Substitute in, but you'll notice before I do that, I'm going to change that back to third form. So x to the power of 4/3, well 4/3 is 1 and 1/3, so it's x to the power of 1 times x to the power of 1/3, which is the cube root of x. So I have x times the cube root of x. It's unfortunate the formatting of the package I've used there, because it does look like x cubed there. Remember, when you're writing cube root, it's a good idea to get that 3 and put it in the v of the root sign, if you get what I mean, to make it obvious we're saying cube root, not x cubed. Why did I do that? Well, the cube root of 5 is not going to be an exact number. If I go to a calculator, I'm going to get an approximation. And certainly if I go 5 to the power of 4/3, I'll get an approximation. But putting it in this form, I'll get an exact value. So I've got 5 times the cube root of 5. I can tidy it all up. I get 15 times the cube root of 5 over 4. I've got the exact amount. Sine, we haven't talked about trig functions yet, but this is where we remember, hang on a sec, the sine curve is an odd function. And you'll notice I'm going from -2 to 2. Whenever you see that symmetry in the limits, just have a bit of a think about the function. Is it odd? Is it even? Can I tidy this up? In this case I can, because an odd function to the power of 5 will end up being odd. Remember, odd times odd will give me even, and even times odd will give me odd. So, power of 5, we're going odd times odd, that's even, times odd, that's odd, times odd, that's even, times odd, that's odd. I've ended up with an odd function. So all of that's 0. I don't have to waste time trying to work out what on earth this integral of sine to the power of 5 is. But the answer is just going to be 0. And that's all we're interested in this question, is what's the value? Again, I see the symmetry, but now I can combine the idea with, hey, just do a piece at a time. I can make this a little bit easier for myself by looking at it and saying, well, hang on a sec, all of those odd functions in there, they'll be 0. I don't have to worry about integrating those. And the even ones, I can go twice from 0 to 1. So I simplify this integral down, and I just say, well, that's going to be the same as 2 times the integral from 0 to 1 of 2x squared plus 1. Now I've only got 2 things to integrate. It's not like the other ones were hard, but think about it. If I had left it that one, I would have integrated and ended up with 4 things. Then there's 4 things I had to substitute in and calculate, and it saves you a little bit of time. Add 1 to the power over the power, substitute in, 10/3 is our answer. Look at this thing called sketching the signed area function. The signed area function, yet another fancy word for primitive function. You remember the primitive function was the area function. That's where we were coming from. We said, oh, hang on, this is the same as the primitive function. So essentially, we're saying the area function will be the integral and we'll have some starting value and going to x. That's our function, whatever it is. Which we know when we substitute in, we'll get fx minus fa. Now I've changed the letter here because what I'm saying is it's the primitive function of this, which, yeah, all right, it is the same, but yeah, technicality. All right, here's a graph of function x. We want to draw a graph of the area function. Now, to make this example a little bit easier, I'm going to assume some things here. I'm going to assume that the area going from 0 to a, I'm going to call it capital A, is actually the same as the area going from A to B, is the same as the area going from B to C, and is the same from the area going from C to D. I'm just going to assume that for the sake of our example. Okay. When I'm setting these up, think of it like a hierarchy of derivatives, and I work my way down. So the original function I'll put on top, the first derivative I'll put underneath it, and if we kept going, I'd say, well, the second derivative graph I would go under that, and the third derivative graph I would go under that. So I think of it like a hierarchy, and I'm working my way down. Now, our function is the first derivative of the area function that I want to draw. So that's why I've placed my number plane for the area function above function x. So in my head, I know the picture here is a picture of the derivative of this function I'm going to attempt to draw. Now I will read off and translate information. What sort of things do I know? Well, I know area A, so when I substitute A into this picture, I'll get an answer of 0. And why do I know that? Here's our definition. Remember, area x was A to x. Well, if I'm going from A to A, then I must have 0 area, because I haven't got anywhere. Because we'd end up with function A minus function A, got to be 0. So I now know that I have an x-intercept on the area function at A. I know that to be true. What else can I tell from that? I can tell that it's going to be a stationary point, because remember, the one underneath is the derivative, and if we have a look, it's equal to 0. So I know the first derivative is equal to 0. On my new graph, this picture I'm trying to get, I know there's going to be a stationary point there. Okay, let's find the x-intercept. What would A0 be? Okay, again, let's go back to our definition. I'll be going from A to 0. A to 0. But hang on, I'm allowed to swap the limits around, but I'll just change the sign. So it would be the same as the negative from 0 to A. Well, let's have a look at the graph. What is it from 0 to A? Well, it's capital A. Therefore, I know the answer to this is negative A. So I'll plot that in. There we are. We're at negative A at the y-axis, the y-intercept. All right. Next key point. Area B is negative A. Well, how do I know that? Okay. Remember, at the point A, the value was 0. I'm now adding on another A, but it's below the axis. And we said if it's below the axis, it has a negative value. So I've now added on negative A from the point A, therefore I've got negative A. Okay, let's plot that. I also know though, we must have a possible point of inflection here. Now how did I work that out? Okay, so B is the value. I look at the derivative graph. But at the derivative graph, I have a stationary point, which means the first derivative of this picture is 0. Well, the first derivative of this picture, we would go down a level, is the second derivative of the graph I'm trying to draw. So the second derivative for the one I'm trying to draw is 0. Possibly we have an inflection point there. Let's now work out C. What have we done? We're now going to add on another negative A. So at area C, we get negative 2A. Let's plot that one in. Okay, it's starting to take shape. Oh, and that'll be another stationary point, because have a look at the derivative. It's equal to 0. I now know there's a stationary point there as well. Okay, so what have we got so far? We've got this y-intercept, we're going up to a stationary point, we're coming down to something that possibly is an inflection point, and then getting another stationary point. We're starting to get a feel for what this curve's doing. Well, let's work out D. Well, D, we've now moved along another A, but it's a positive amount. So negative 2A, add on A, I'm back at negative A again. Plot that point. What happens after D? Well, after D, I know this function is increasing. Well, how do I know that? Have a look at the derivative. The derivative is always going to be positive from that point on. And we said when the derivative is positive, the function is increasing. So I know this will just keep going up. There's my graph. Now, we can now look at it in a different way. I don't know if it is a parabola, but it certainly looks like one. It's got that sort of shape to it, a quadratic. If you were going to integrate a quadratic, you will get a cubic, because you add 1 to the power. And yeah, my picture does look like what I would recognise to be a cubic. So it kind of backs up that information. So that's what we call the signed area function. Again, it's another thing we look at in a bit more detail next year, of actually drawing derivative graphs and things like that. 5C and 5D, playing with the definite integral.